This is Solomon Culver. I'm a hospitalist at Ohio State University, and this is the first of a series of lectures that are leading up to an analysis of the paper Restrictive or Liberal Transfusion Strategy in Myocardial Infarction by JL Carson. This is a New England Journal article that is just a really great opportunity to review concepts from evidence-based medicine and hopefully learn a few new ones as well. The name of this lecture is Statistical Significance and Prespecified Outcomes. But before we get started, would you please just like and subscribe below so you can help my channel out. So a lot of people may not realize this, but there are two major statistical paradigms that statisticians use today. The first of the two is called the Bayesian paradigm, and it's actually very intuitive. Essentially what it does is take a collection of data and then from that collection of data tell the reader what they ought to believe. Now, unfortunately, it's not possible to tell a person what they ought to believe based on some limited data without first knowing what they already believed based on the lifetime of experience and information that they had gotten before the study. So, in order to do a Bayesian analysis, you have to first specify what your prior beliefs are. And because rational people can have different prior beliefs, that means that two rational people can have different conclusions from the exact same data. This is not perhaps ideal for the system of medical research because we want to be able to say that a trial was positive or negative, and we don't want to make it relative to what the reader's beliefs before the trial were. Because of this significant hurdle to interpreting Bayesian studies, medical research does not really use this approach at all, almost, for better or for worse. Now, the type of statistics that we do use in medical research, and probably what you've studied before in college, is called frequentist statistics. Now, this has the benefit of not really requiring prior beliefs. Those don't factor into the analysis, but it has the downside of also not being able to tell us what is rational for us to believe. Instead, the frequentist paradigm, it's really about creating experiments or designing estimators that will probably work. It's not about looking at data and saying what is probably true, which is the Bayesian approach. Now, this focus on designing experiments and estimators rather than focusing on data and belief, it leads to a lot of counterintuitive results that I'm sure a lot of you have struggled with over the years. Clinical trials can confuse a lot of doctors because we all want to interpret them as being Bayesian. We want the trial to tell us what we should believe, what's rational, but that's not what they are. The clinical trials that we create are more like machines that are designed to make estimates or to prove hypotheses, and they're designed with known probabilities of error. So like any machine, it's basically done. Once we design it and we ship it out, all of the specs are determined. And when we use it, we get a result and we say the trial is positive and it was produced with a procedure that usually works. We can't say the trial is positive, therefore the hypothesis is probably true, or therefore I should believe in the result, because we can't say what you should believe until we have your prior beliefs. So that's a big difference between the Bayesian reasoning that we think we're looking at and the frequentist reasoning that we have to adapt ourselves to. So it's kind of funny to say that an experiment usually works when we know that it's only really done one time. But what that means to say is that there's an element of randomness in every clinical trial. And the randomness comes from the patients that are sampled. And it's possible for the patient population that's sampled to just happen to be that it would make an ineffective treatment look like it was effective. and that is called the type 1 error. And it's also possible that just by chance, patients were sampled that would make an effective treatment look like it was ineffective, and that's called the type 2 error. So when we say that a trial is designed so that it will probably work, it means to say that it should give an accurate outcome across a wide range of different sampling possibilities. So the type 1 error rate is the probability that the investigators will reject the null hypothesis when it's actually true. So this is a value that really only makes sense in situations where the null hypothesis is correct. When the investigators set the type 1 error probability, what they're also doing is determining how difficult it will be for them to find significance in their study. If they are going to accept a 5% probability of type 1 error, then they can reject the null hypothesis only when the p-value is less than 0.05. But if they would accept a slightly higher false positive rate, like 10%, then they would only need to have p-values less than 0.1 in order to reject the null hypothesis. So this makes it easier for them to have a positive study, but it also makes it easier for that positive study to be falsely positive. So that is the hypothesis testing aspect of frequentist statistics, but a lot of the studies that we are used to reading don't really use hypothesis testing so much as they use confidence intervals. Now, a confidence interval is an interval that the investigators will calculate during the course of the study, and it's designed so that that interval has a 95% probability of capturing the true value. Now, of course, so that means to say that if you repeat that study over and over and over, 95% of the time, the interval that's calculated will contain the value that they're looking for. But of course, they really only do the study one time, and we can't say that any particular interval that they come up with from that study has a 95% probability of containing the true value, because it either does contain it or it doesn't. That 95% probability, it's a probability about the experiment. It's not really a probability about the data itself. So all that they can really say about any confidence interval that they produce from their study is that it was calculated using a procedure that had a 95% probability of success. Therefore, after they calculate it, they can feel 95% confident that it actually does contain the true value, and that's why we call it a 95% confidence interval. On the right-hand side of the slide here is a situation where they actually did repeat an experiment, a 95% confidence experiment, 100 times. And as you can see, 4 of the 100 intervals that were created actually did miss the true value. So what can we say about those intervals? The green intervals have a 100% probability of containing the true value because they do, and the red intervals have a 0% probability of containing it because they don't. But every interval that's listed here is a 95% confidence interval because it was produced by a procedure that had a 95% probability of working. So now that we have this perspective of clinical trials as being designed to measure something within pre-specified probability of error, then we can think about a few specific examples to kind of see how that comes together. So let's first think about a study that wants to look at 10 distinct clinical outcomes with each one has its own statistical test with a 5% type 1 error rate. Then the probability that at least one of those tests will have a false positive is actually 40%. And if we're trying to create a test that will, a clinical trial that will probably give us a correct result, then we really won't be happy with a clinical trial that gives us a wrong result 40% of the time. So what we need to do is revise each of the error rates of the 10 tests so that the trial in aggregate altogether only has a 5% error rate. And in order to do that, we can make each one of those tests, we can give it a 0.5% error rate so that the clinical trial as a whole still maintains that error rate of 5%. Now the cartoon up here in the corner, it's about a hypothetical study that sees if we can link jelly beans to acne. Now, if you just do that study, you're going to get a negative result. There's no link. But if you instead separate the jelly beans into each of 20 colors and do a separate test for each color, then on average, you're going to get one false positive result each time you do that study. And in this case, it said the green jelly beans were linked to acne. The problem is that is not true. That is not a 95% confidence test. In fact, you anticipate one error like that each time you would do the study. So we want to do an experiment that has only a 5% chance of false positives. And we know that the probability of getting a false positive depends on the number of outcomes that we're testing. So that means that if we're going to set the alpha levels of each of those tests precisely in the way that gives us a 95% confidence experiment, then we have to know up front exactly what is being tested and how many things are being tested. And once we do that, once we know that, and the experiment is designed, then we can't deviate from that protocol, because any deviation leads to it's a different experiment. If you add things that you didn't intend to add, then you're not doing the experiment as it was designed, and therefore you can't be 95% confident of the results. So any test that's done that's not pre-specified in the trial is no longer a 95% confidence experiment, and we have no frequentist way of interpreting the meaning of those post hoc tests. So to summarize what we've talked about so far, clinical trials are tools that are designed to measure some effect with some pre-specified probability of error. And we want to design trials so that the probability that they find a positive result that doesn't exist is only 5%. Therefore, we have to pre-specify each of the tests that we're going to do and arrange each one so that their combined error probability is 5% or less. Now, any test that's not pre-specified in that way, that we do anyway, can't really be interpreted in a statistical way, because it wasn't part of any experiment that was a 95% confidence experiment. So now we come to the trial that we're building up to, which is the MINT trial. And this is a trial that was designed to look at transfusion goals in patients with acute MI. And the specific question was, is it beneficial to transfuse these patients to a goal hemoglobin of 10 as opposed to the goal of 7 or 8 that we're currently using? And there was one pre-specified statistical test in the study, and it was a composite outcome of recurrent MI or death at 30 days. So this was a 95% confidence experiment with respect to that outcome, that one single primary outcome. And for that outcome, there was a point estimate of 1.16, and the confidence interval went from 1 to 1.35. Now, that means that it contained the point 1, which is the point of no effect. And therefore, we can't really say that we're 95% confident that the more liberal transfusion goals led to better outcomes. So from that perspective, it was a negative trial. However, there was a different post-hoc outcome that was cardiac death. Now, they said they pre-specified cardiac death in that they told everyone they were going to measure it, but it wasn't pre-specified in the way that they corrected anything for multiplicity. So it is a post-hoc test, but it was a positive one, was it? The point estimate was 1.74, and that quote-unquote confidence interval went from 1.26 to 2.4. But that wasn't a confidence interval because it wasn't produced by a method that had a 95% probability of working. Therefore, it really has no direct meaning except perhaps to, motivate a future study if somebody wanted to do that. So our final conclusion is that the MINT trial did not find a statistically significant benefit with respect to its primary outcome, its only pre-specified outcome of death or myocardial infarction. There was a post hoc analysis that seemed to show fewer episodes of cardiac death, but that finding cannot be given any level of confidence because it wasn't pre-specified, and therefore it has no real statistical meaning.